Assalamu alaikum wa rahmatullahi ta'ala wa barakatuh. I would like to share with you our work. The title of our work is the performance investigation of the solar chimney power plants in the desert area of Algeria, exactly in the region of the Tamarast. All authors of this work from the University of the Tamarast. Before to start our presentation, I give you the outline of the presentation. I will start by the introduction. Within this introduction, I give you why we need the solar chimney or the solar energy, and we define what is the solar chimney and how the solar chimney works, how does the solar chimney works, and we finish the introduction by the objective of this work, and we pass to the physical model to explain the physical model, and after that we give you the our results, and we finished our outlines or our presentation by the conclusion. Let's start by the introduction. In the many parts of the world, there is the growing awareness that some the alternative energy sources could have the important role to play in production of the electricity. However, solar energy represents totally non-polluting energy resource that can be utilized economically to supply men's energy needs for all time. Here I give you the definition of a solar chimney. The solar chimney, we call it also the solar updraft tower, is the renewable type power plant. The solar updraft towers are like the inverted funnel with wide skirt to collect air to the then turn turbine in the tower. Here we try to explain how does the solar chimney works. When the incident solar radiation hits the air under large transparent collector roof, the temperature difference causes pressure drop over the height of the chimney, resulting in an upwind which is converted into the mechanical energy by the turbines and then into the electricity via the conventional generator. The main objective of our work is to investigate the performance of the solar chimney plants in Algeria desert area, exactly in the Tamarast region. Here I would like to present to you our physical model. In order to analyze the heat flux and the transfer related to the buoyancy in the solar chimney, we use the geometric parameters of Manzaranas power station. The height of the chimney of this prototype is around 194.6 meters, and the diameter of this chimney is around 10.16 meters. The radius of this collector is around 122 meters, and the height of this collector from the ground is around 1.85 meters. The turbine is installed on 9 meters from the ground. This configuration guides the airflow in the vertical direction before the turbine location section. We use here the thickness of the ground is around 5 meters. Here we try to explain the second model, which is based on the reference plant specifications in the previous slide. In order to improve the power output of the solar chimney power plant, we have added the secondary roof under the main roof. By the way, the length of the secondary collector is about the 107.75 meter, and the height of this collector around 0.5 meter. And the properties of this secondary roof is same or similar as the main roof. Here is the third our model we have implemented. As you see here, is same as the previous one. The modification we have done, just we add the third collector. Why they added here the third collector? To improve the power output. Here I would like to share with you our results. Using the CFD software, we simulated 3 systems we explained before in the previous slides. As you see here, this graph shows us the power output in terms or over the year from January to December. As you see from this graph, this graph shows us the high power output during the June and July month. And the last model, which is called second and third collector roof, give us the highest power output. This graph give us the variation of the power productivity versus time for the June month. As you see here, this graph shows us the power output versus or in terms of over the day from 6 o'clock to 6 o'clock p.m. As you see here, the highest power output recorded at 12 o'clock, and the third model give us the highest power output around around 80 kilowatts. In conclusion, the feasibility of implementation of solar chimney power plants was investigated in the Tamarast region. The reference plant, secondary collector roof, and the second and the third collector roof systems have been implemented in the Tamarast region. And the last one, we found that our system has produced the highest production of the electricity, which is the secondary and the third collective roof system. At the end, I would like to thank you.